Okay, we can go.
Okay, good morning to everybody. This event called the Matemairacorana was first held in the Department of Mathematics in the University of Recife in Pernambuco, and it lasted for the whole month. We invited many people who could spend from 1 week to 1 month, and every day we had a talk. The rest of the time was to discuss among the participants.
That was in what year, Hildeberto?
What?
Which year that was?
I don't remember, but I think it was in 2005. Maybe we remember the year.
Yeah, I think so.
2005?
2005.
Okay, Eduardo said.
2005.
What?
The early months, January, February.
Mm-hmm. Okay, and then it was successful in the sense that it allowed the people to come and talk for the whole year and participate in seminars, and we had just one talk per month. And then we got this event realized again with the by suggestion of a group of people in Recife and also in France, Alain Bouy in France, Alain Chancinet, Annette Cavalcanti, Lúcia Brandão, Eduardo Leandro, and others, and they did that during my 80th birthday. Then it was repeated the following year for a shorter time, and there were some sessions, and now we have the third, what Jai called it, the third turn, which is still in a chaotic periodicity. But I think he has the idea that these talks will continue in other occasions, but not maybe with the periodicity of one per week as the first one. So that's what I could say about the Matemairacorana. Thank you.
Wonderful. So it's I think now is 11:05. I think I can make a very brief introduction of Professor Wisdom, and then Annette will take over with the rest of the talks and also of the questions in the end. So everybody certainly know Jack in the field. He's one of the leaders in the field. I had the privilege to meet him in the early 80s when he was a very young tenure-track professor. He was very proud to be in the same place where Edward Lorenz has been a professor. I don't know if Lorenz was still there. Maybe he was almost retiring. But Jack was very proud of, he was in the right place at the right time. And I think he was the pioneer of finding the chaotic phenomena in the solar system. And since the audience here is of people in celestial mechanics, I don't need to say anything else than saying that he got all the main prizes in the areas, the Urey Prize, the Broward Award, and he has an asteroid under his name, etc., etc., etc. And from the point of view of the area that the abstract people knows, he one of the persons that started the symplectic integrators, and he made them work in practice, which is sometimes from the theory to practice, there's a big distance. So I think that's enough of a presentation. So Annette and Jack, please go ahead. And I recommend people for during the talk to take the images and the microphones off so that we can enhance the speed of the internet. And after Jack is done, then we can put the images and sound again. Thanks. Annette is with you now.
But actually, you can start, Professor Jack.
I should begin now. So thank you for inviting me, and I think it's very pleasant to see you all, many friendly faces. So I'm going to present the paper that we published last September in Science on the origin of Saturn's obliquity and young rings. And it's done in collaboration with these folks. There's my graduate student, Roland de Boek, Burkhard Militzer, who's professor at Berkeley, Bill Hubbard, who's emeritus professor at Arizona, Francis Nimmo at Santa Cruz, his graduate student, Brenna Downey, and Richard French, Dick French, who's at Wellesley, also retired. So, here we go. So the work addresses two mysteries and finds that the solutions of the two mysteries are linked. Saturn is, the spin axis of Saturn is tilted by about 27 degrees, and this is more than would be expected if Saturn formed by accretion from a protoplanetary disk or through later collisions. The second problem is that it's long been suspected for about 40 years that Saturn's rings are only 100 million years old. This is a result that my advisor, Peter Goldreich, and his postdoc at the time, Scott Tremaine, realized while I was a graduate student. And this, they were estimating ring satellite torques, but there's an independent line of evidence, in fact, several independent lines of evidence that the rings are only about 100 million years old. And that's that there's a constant bombardment of micrometeorites of the rings and they're ice rich, so that micrometeorites should darken the rings. And so by modeling the brightness of the rings, you get an independent estimate of about 100 million years. So a summary of what we're doing is that we use Cassini spacecraft observations, a number of different aspects of Cassini observations, and numerically modeling to conclude that both of these mysteries have a common explanation in that Saturn once had an extra satellite, which we named Chrysalis. We'll explain the name later. And the presence of this satellite allowed the obliquity of Saturn to develop from a spin-orbit precession resonance with Neptune. And the orbit of the satellite became unstable and had a close encounter with Saturn and was ripped apart, and that formed the rings. That's the basic overview of the story. So spin-orbit precession resonance has been known for a long time. In 1693, Cassini discovered that the spin axis of the moon precesses at the same rate as the normal to the orbit of the moon. So they're in resonance. And this is an example of a spin-orbit precession resonance. There are actually many cases of spin-orbit precession resonances in the solar system, but I won't go through the full history. So in the case of the moon, the obliquity of the moon, the tilt of the moon from its orbit, depends upon the precession frequency of the orbit. And as the moon evolved away from the Earth, the precession frequency changes, the rate at which the node of the moon precesses changes. And as a consequence, the lunar obliquity changes with time. This was pointed out by Ward in 1975. Here's a figure from Ward's paper. This shows the lunar obliquity, the tilt from its orbit, in degrees as a function of the semi-major axis of the moon. So it's, in a case of a uniformly precessing orbit, there are four equilibrium states called the four equilibrium Cassini states. And it's thought that the moon initially started in state 1 on the left. Can you see my pointer?
Yeah, we can.
Okay. On the left in Cassini state 1, as the moon moved outwards around 30-something Earth radii, the state 1 became unstable. It went through a period of instability and settled onto state 2, where it's found today. But the main point of the figure is that the obliquities of the moon can be large as the precession frequencies change. So the rate of precession of the spin axis of Saturn is nearly resonant with the rate of precession of Neptune's orbit, which is already noticed by Harrison and Ward 40 years ago. And changes of parameters controlling the precession rates can lead to the large obliquity of Saturn. So it was proposed by Ward and Hamilton in 2004 that the Saturn's obliquity could have arisen in the early solar system as the rate of precession of Neptune's orbit changed, as the mass distribution changed, as planetesimals were ejected from the solar system. That changed the rate of precession of Neptune's orbit. But recently, it's been discovered that Titan, the largest satellite of Saturn, is rapidly migrating outwards, around 11 centimeters per year. And this suggests a new possibility for how the obliquity of Saturn could have arisen. So let me just remind you about precession. The spin axis of an oblate planet in a fixed circular orbit regresses at the rate of just alpha times cosine epsilon, where epsilon is the obliquity, the tilt of the spin axis. And the precession constant is alpha, is this formula. N is the orbital frequency, the mean motion. Omega is the rotation rate. J2 is the second gravitational moment. And lambda is the reduced moment of inertia, C over mr squared. And that's, if the planet has satellites, there's two modifying factors, the Q and the L. Q is more important than the L. So the Q is a sum over the satellites, and each term is proportional to the mass of the satellite and the square of the distance of the satellite from Saturn. And so the satellites contribute to the precession of the system because the sun acts on the satellites and they're locked to the equator. So the precession depends upon the presence of the satellites. And for Saturn, the precession is actually dominated by the contribution of Titan. So Q is around 0.05 and J2 is 0.016. So the presence of Titan is the most important factor. And as Titan is moving outwards, that factor changes with time. So the precession constant changes with time. So we noticed this. I was working with Francis Nemo on, in general, the tidal evolution of the satellites, and we noticed that this might be an explanation of the obliquity of Saturn. But we were scooped by the Salenfest, the French group Salenfest, and they basically pointed out that the obliquity could have arisen through this resonance with Neptune. And so this is a figure from their paper. The initial obliquity of Saturn is, in this calculation, is on the order of 5 degrees. That on the top abscissa is the precession constant. The precession constant increases as Titan moves outwards. And there comes a point where it gets captured into the spin orbit resonance. At low obliquity, the capture probability is certain. And then the subsequent evolution, the obliquity rises as you stay locked in the resonance. And this was a possible explanation for the obliquity of Saturn. A problem with this explanation is that the moment of inertia, which appeared in the denominator of the precession constant, was uncertain, they thought, by perhaps 10%. And so the green bars indicate an idea of the uncertainty in the precession constant. So that uncertainty meant that you didn't know whether it was in the resonance or out of the resonance. So to make progress on the problem, we had to determine the moment of inertia. So mostly in my career, I've studied dynamics, but I also from time to time dabble in a few other things. And I dabbled in interior modeling a while ago. So we have to determine the moment of inertia of Saturn, and we do that by finding models that match the gravitational moments as determined by Cassini. So you all know what the J's are, but this is just a review for any who might not. So the gravitational moments are, the even gravitational moments are known from J2 through J12 by Cassini. So 40 years ago, Hubbard wrote a paper in which he said that the behavior of the moments, the high moments, could be a diagnostic of whether there was differential rotation in the planet. So this shows the moments with the scale factor of the rotation parameters set to some power. And in this way, plotting in this way, the moments should level off as the degree is large. And Hubbard pointed out in '82 that this leveling off would not occur if there was differential rotation. And that was actually, I think, one of the main motivations for Cassini and Juno to measure the high order moments of Jupiter and Saturn. So what was found with Cassini is that the moments did not level off. And you can see the pink area that is marked the effect of differential rotation. So the big red circles are the Cassini measurements, and then the diamonds are the model of Militzer, Wall, and Hubbard, which uses all the physics equations of state and includes differential rotation. And you can see that you can match the moments with their model. So in order to make progress on the origin of the obliquity, we made new models to find interior models that match the gravitational moments, and from those we computed the moment of inertia. So we used 4 models. The first model is the kitchen sink model that was mentioned on the previous page. That's fitting J through J12 with differential rotation and physics-based equations of state determined with quantum calculations, and the method they used to solve the hydrostatic structure is the method invented by Hubbard, the concentric Maclaurin spheroid method. And then we used 3 other methods to get additional information and find out how uncertain our conclusions were. These methods only fit J2, J4, and J6 without differential rotation. And the first method is the one that I developed in '96, but never published. And we call it the consistent level curve method. It's actually not as easy as you might think to solve for the hydrostatic structure of a planet. But one thing I did in that paper, which I thought was cute, was I was impressed at how uncertain the physics was. At the time, it wasn't known whether the discontinuities, whether the phase transition between molecular and metallic hydrogen was a discontinuous phase transition or not. And so I wanted to determine interior models without all that uncertainty. And so I introduced the idea of making abstract polynomial equations of state. So I got rid of all the physics and then solved for the interior structure given only the observational constraints of the gravitational moments. So that's one method we're going to pursue. And then the next one is the CMS method using physics-based equations of state, but without differential rotation, only fitting J2, J4, and J6. And then Bill Hubbard also did just a cruder model, a 4-layer CMS method. And the advantage of this is you can get some idea of the uncertainty of the result. So here's in a sense, the central plot of our paper. So this is rotation period on the abscissa and the normalized angular momentum on the ordinate. And normalized angular momentum is the moment of inertia, the main uncertainty, the main parameter we're trying to determine, multiplied by the rotation rate to give an angular momentum, and then it's normalized by a factor to make it dimensionless. And you can see the 4 models on the plot. So the bottom curve, the red curve, is the kitchen sink model. That's the one with differential rotation matching the moments up to J12. And on the top, the yellow results are my method using physics-free equations of state. And the blue diamonds are the CMS method with physics-based equations of state. And I think it's just pretty remarkable that the agreement of the blue and the yellow. So you don't have to include the physics, but if you include the physics, maybe it's more reliable. It agrees quite well. And then the green shaded region indicates the more crude 4-layer models, which are randomly selected so you get an idea of propagating the errors. The vertical pink band is the estimated rotation rate, and that's determined by matching the flattening of Saturn, and independently by using what's called ring seismology, which looks at detailed features in Saturn's rings, and from that you can determine the rotation rate. And so we have the rotation rate, and we have models that determine the moment inertia. Now, at the top of the plot is the horizontal gray band, which is the critical value for whether you're in the resonance or not. So if you're below the gray band, you're not in the Neptune resonance. And if you're above the gray band, you're in the resonance. In the resonance doesn't mean you're at the center of the resonance, only that the resonance angle is librating. So all of our models fairly tightly constrain the moment of inertia. They're all consistent with one another, and they show that the system is not in the resonance. So this is rules out that the conclusion of Salenfest that the obliquity of Saturn arose by the Neptune resonance, because they predict that the system would still be in the resonance. And also the scenario of Ward and Hamilton also predicted that you would still be in the resonance. So it would be nice to understand why the differential rotation result is lower than the result without differential rotation. And I have a few slides to try to motivate that, but I'm not sure it's that's key for this. So, but I'll present them anyway. So if you take 4 spheroid models with measuring only matching J2, you get the yellow curve, and you can see you could get values of the moment of inertia that are above the critical value. But just adding the matching J2 and J4, you're already restricted to values of the moment of inertia less than the critical value, and then you add J6, and that tightens the estimate of what the moment of inertia is. And then the fact that you use 4 spheroids, it doesn't matter if you use a variety of spheroids, you get consistent results, and there's a gap between the moment of inertia and the critical value. And then why do the results with differential rotation lower the moment of inertia? And that's because adding differential rotation makes an extra contribution to J6, which is not relevant for determining the moment of inertia. So if you subtract that contribution of J6, it lowers the moment of inertia, and that's documented in this figure. So we think we understand the moment of inertia, and we think it's we have reliably determined it. It's not at all uncertain by 10%. The uncertainties are well less than 1%. Now the gray curve is determined by numerical integration. You can try to estimate it analytically, but when you try to do that, you find a host of little tiny effects that you may have trouble estimating. So we determine the moment of inertia by doing a just brute force numerical integration of the Saturn system with all the main satellites from Mimas to Iapetus. We modeled the rotation of Saturn as a rigid body. The gravitational moments, we included J2 through J6 and the sun, and perturbations from the 4 outer planets. So it's kind of a kitchen sink dynamical model. The initial conditions and parameters are from JPL, which were determined by analyzing Cassini spacecraft. And then we used the integrator, the in-body mapping method that I developed in '91. It's a symplectic integrator, if you prefer that terminology. And we used the axisymmetric method that my graduate student Jihad Touma developed in '93, and we used that to show that the tilt of Mars was chaotic. And then we also used the symplectic corrector, which is a way of removing integrator-induced oscillations. So it's kind of fun. In our integration that showed that the solar system evolved chaotically, I developed the corrector several years later and was able to reduce the integration error by several orders of magnitude after the fact without redoing the calculation. And then we used the hierarchical Jacobi constant coordinates to split the Hamiltonian and eliminate the center of mass. And they're convenient for this problem because you have a hierarchical system of masses. The satellites orbit Saturn orbits the sun, other planets orbit the sun, and the hierarchical Jacobi coordinates are a natural way of developing integrators. We use a step size of order 0.06 days, which is pretty small. And computers are fast enough that you can integrate for 50 to 200 million years. In an integration of 50 million years, the energy and angular momentum are conserved to better than a part in 10 to the 10. They typically, in these integrators, grow as the square root of time. Our integrator runs at the rate of about 5 million years per day, so a 200 million year integration takes about 40 days. So we've this plot, we've deduced that the system is not in resonance. So we ask, how did it get out of resonance? Well, the system is very close to the resonance. It's only 1% away from the critical value. And we argue that that's too close to be a coincidence. So, for instance, changing the semi-major axis of Saturn, which is not special, by 5% results in a 15% change in the precession constant. Similarly, if you change the masses or semi-major axis of Uranus or Neptune, that can make large changes in the precession rate of Neptune. So to be only 1% away, we argue, means that the precession resonance with Neptune was definitely involved in the raising the obliquity of Saturn. So then how did it get out? The fact that it's very close, well, yes, it recently escaped, and that's indicated by the close proximity. Because of the continued tidal evolution of Titan, the distance from the resonance increases with time. So it had to have escaped the resonance relatively recently. So we identified two possibilities. One is that the system passed through some orbital resonance among the satellites that possibly changed the parameters of the satellite orbits, and that would modify Q, because the Q is a sum over satellites, and the orbit properties enter into that. And we ruled this out by doing several 200 million year integrations of the tidally evolving system. I initially wanted this to work out because I wanted a non-catastrophic way of explaining the obliquity of Saturn, but it didn't work out. We didn't; those integrations didn't reveal a way of getting out of the resonance. So then we proposed that there used to be an extra satellite that was lost, and as it was lost, the precession constant changed. That's because one term in the sum for Q was removed. So there's a sudden decrease in the value of Q with the loss of the satellite. So we not only do numerical integrations, but we use a resonance model. This is helpful to understand the dynamics, and also the numerical integration is limited to it in practice to a time of order 200 million years, and we'd like to extend it to more distant times, like 1 billion years in the past. So we do that with the resonance model. And the resonance model is a 1 degree of freedom Hamiltonian system for the spin of a rigid body rotating about its largest moment of inertia in an orbit that's evolving due to planetary perturbations. And a key ingredient is, again, the same precession constant that I mentioned before. And the contributions to Q are proportional to the mass of the satellite, the square of the distance from Saturn, but it also has factors that depend upon the obliquity of Saturn and how far away the satellite is from Saturn. So the model is actually somewhat internally inconsistent, and it's approximate, so it can't substitute for the full integrations, but it's still useful. It's approximately right. So here's a summary of our scenario involving this lost satellite, this loss of Chrysalis. So the precession constant's on the abscissa, and we start at 0.1 at low obliquity, and then we evolve as Titan evolves outwards. You evolve to 0.2. At that point, you get captured into the resonance, and then the obliquity rises. And this is the same scenario that Salenfest described. But in our case, the obliquity actually overshoots the actual obliquity of Saturn. And at 0.3, you have the loss of Chrysalis. So there's a sudden decrease in the precession constant. So you go from 0.3 to 0.4. And then from 0.4, you evolve forward in time. You again pass cross the resonance, but at higher obliquity, the capture probability is close to 0, so you pass through the resonance, and that allows you to come to where you are today at 0.5. If you view this in terms of time, you get additional insight. So the top curve is the obliquity as a function of time. And again, you start at low obliquity, and you get captured into the resonance. And you can see the capture into the resonance in the lower panel, which shows the resonance argument. The resonance argument in this case is the longitude of the equator, the ascending node of the equator on the invariable plane, minus the descending node of the longitude of Neptune on the invariable plane. So the difference of the equator and Neptune longitudes. And you can see initially the resonance argument is circulating. And then at this point where you get captured, the resonance argument switches from being circulating to librating, oscillating. And with this choice of angles, it oscillates around 0. So that's the red curve is the forward evolution using the resonance model to high obliquity. The blue curve shows the result of a full numerical simulation going backwards in time from the present. And going backwards in time, you get you approach the resonance, and you actually cross the resonance. You can see a crossing because the resonance argument goes from circulating in one direction to circulating in the other direction. And if you want the backward integration to agree with the forward integration, you have to match the two curves. And you can do this because the red curve is oscillating around 0. The blue curve can only join that curve if the blue curve is near 0. So one way to match the two is you find a 0 crossing of the blue curve that crosses at the same time as the red curve. So this is the point that we suggest chrysalis was lost, and you went from the blue curve with the red curve with chrysalis to the blue curve without chrysalis. And in time, the obliquity evolves continuously. So the backward evolution, you cross the resonance to higher obliquity, and then you match join the red curve with chrysalis. The gray curve indicates what would have happened backward in time without chrysalis. So that's our scenario. And to connect to the current system, chrysalis placed between Titan and Iapetus, that's where we found it was possible to do match the solutions, must have a particular mass to take you from the present to before chrysalis was lost. It would be close to the center of the resonance. It had to be a mass in the range of 30 to 60 times the mass of Mimas. The rings, by comparison, was also measured by the Cassini spacecraft to be 0.4 times the mass of Mimas. And we basically know everything about where chrysalis was. So chrysalis must have been lost between 100 and 200 million years ago, depending on the rate of tidal evolution of Titan. There's some uncertainty in that 11 centimeters per year. And so we did a variety of integrations, and in this simulation, chrysalis was lost 160 million years ago. But if you adjust the rate of tidal evolution of Titan, you find a range of values. So basically 1 to 200 million years ago. And this neatly corresponds to the suspected age of the rings it's been suspected for 40 years. So how can chrysalis be lost? Well, it can be lost. Titan is moving outwards, so the ratio of the orbital periods of Titan and chrysalis are changing. And it can be lost if Titan-chrysalis pair encounters a very unstable resonance. And the first resonance the first strong resonance that's encountered that's first or second order resonances, is the 3-to-1 Titan-chrysalis resonance. So that's where the orbital period of chrysalis is 3 times the orbital period of Titan. And it's well known that 3-to-1 resonances can be very unstable. So here's an example of simulation showing Titan evolving into the Titan-chrysalis resonance. This is the eccentricity of chrysalis versus time. And you can see that, once it gets into the resonance, the chrysalis begins to evolve or Titan chrysalis pair begins to evolve chaotically, and very quickly on a time scale of a few 100,000 years, the eccentricity gets close to 1. So it's dramatically unstable. So to study what the typical evolution, typical outcome was, we integrated 370 cases to see what this chaotic evolution looked like. This is an example of such an evolution. So this is the eccentricity of Chrysalis versus the semi-major axis of Chrysalis. And in the beginning, Chrysalis is at low eccentricity. It encounters the resonance. The resonance is a chaotic resonance. The system evolves just through chaotic dynamics up to higher eccentricity. And as is well known, the width of the resonance increases as the eccentricity increases. And then at some point, the eccentricity gets large enough that it begins to have encounters with Titan and Iapetus. At that point, there's a combination of chaotic dynamics and scattering dynamics. And so on the plot on the right, it shows an expanded scale. So the plot on the left is just this needle of points here. And then, and I think I forgot to mention that the time is on the right, is in the color code. And so after it begins to scatter, the eccentricity continues to rise, the semi-major axis rises, but the distances of close approaches are actually decreasing. So the outcomes of these simulations, 390 simulations, are either there's a grazing encounter with Saturn, and we just define that to be a distance less than 2.5 Saturn radii, which is close to the Roche radius, and forms the rings. Sometimes Chrysalis is ejected from the system, or it could have a collision with either Titan or Iapetus. And a close encounter with Saturn would likely cause it to break apart. If Chrysalis is made predominantly of water ice, like Iapetus, then the debris could have formed the rings. There's a possible problem. Iapetus is not totally made of water ice, so you do have to lose the rocky component by some method. There are simulations of formation of the ring by the breakup of an object. We don't actually simulate that ourselves, but we rely on those the existing simulations. So of the 390 simulations, 19%, 75 of them, had a close encounter with Saturn and thus could explain the Obliquity ring. So we have a 20% likelihood of, so it's not an unlikely outcome to form the rings. We found, one of the reviewers of our initial manuscript said, well, what about Hyperion? Does Hyperion survive? Hyperion is a small satellite that tumbles chaotically. It's in between, it's in an orbital resonance with Titan, a 4-3 orbital resonance. And the referee asked, can Hyperion survive the fact that Chrysalis is bouncing back and forth between Titan and Hyperion? So we redid our calculations, including Hyperion. We found that of the 390 simulations, 90 left Hyperion in an orbit similar to its present orbit. And in fact, many of those left Hyperion in the orbital resonance with Titan. So again, of these 90 results, 21% became hyperbolic, 18% had a grazing encounter with Saturn. And so we found basically 18% of those that left Hyperion in the right orbit and 19% of those where we didn't consider Hyperion. So it's good to get Hyperion in the right, to know that we can preserve the orbit of Hyperion, but the probability of making the rings is independent of whether we deal with Hyperion. Another outcome is another 40-year puzzle in that it was pointed out by Sagan and Dermott around 1980 that the eccentricity of Titan's orbit is anomalously large. If tidal dissipation in Titan should damp the eccentricity with time. And so the fact that it's 0.0288 needs some explanation. So the red vertical bar indicates the actual eccentricity of Titan. And then the histogram shows the eccentricities as a result of our simulation. So Chrysalis repeatedly encounters Titan has close encounters, and that changes the orbit of Titan a little bit. And in these simulations, the eccentricity of Titan started with 0, and the outcome after Chrysalis has the close encounter with Saturn. The eccentricity of these are the histogram of the eccentricities, and you can see the histogram has a peak close to the observed eccentricity of Titan. So it gives a natural explanation for how the eccentricity of Titan came about. So that's a fun thing. So we, as one reviewer said, we have one hypothesis that there used to be an extra satellite, and we explain from that one extra hypothesis that the fact that Saturn is tilted, that Saturn has rings. We explain the age of the rings, and we explain the anomalous eccentricity of Titan. So this is so Saturn was once in the Neptune resonance. It obtained its obliquity as Titan migrated. It escaped from the Neptune resonance because of the instability of the orbit of Chrysalis. It had a close encounter to form the rings, and the required timing, there's no uncertainty in where Chrysalis was. It had to have been in the 3-to-1 resonance with Titan, so we know where Titan was at the time, so therefore we know where Chrysalis was at the time, and we determine the mass by the requirement that we were once at the center, in the center of the resonance, so we know the mass, the eccentricity, and everything there is to know about Chrysalis. And then the age of the rings is anchored to basically 2 measured quantities: the rate of Titan's orbital expansion, which is measured by two different independent estimates from Laney. One is astrometry, Earth-based astrometry, and the second is analyzing the close encounters of the Cassini spacecraft with Titan. And they both give compatible answers, but they're one is more accurate than the other. And then the moment of inertia that we determined by modeling the observed gravitational moments, also determined by Cassini. So why do we call it chrysalis? I hope this is not too goofy. As a butterfly emerges from a chrysalis, that's a stage in the development of the butterfly, the rings of Saturn emerged from the satellite chrysalis. So that's my end of my talk. Any questions or comments?
Agora vou ter que voltar. Ver a câmera aqui.
Should I remove the summary, or I'll leave the summary? So as I commented with Jair, this is sort of a bookend effect. I started out studying the motion of asteroids in 3-to-1 resonance with Jupiter and found chaotic behavior and large eccentricities. So it was kind of fun to return to the 3-to-1 resonance for this problem.
Jack, I would like to make propaganda of some sites which had commented your recent work about this, and there were news in many places. I found one now that I'm going to share in the public chat, but perhaps later you can send some more other ones that we could also comment with students and all. I think as several of your other works, they got some reviews, not only in the scientific community, but in the general press. So, and it's exciting that it happens in science, and not everybody is like that. But in this one that I saw, I'd like to comment. It mentions that in the next 100 million years, the rings may disappear. I didn't get that. Why they would? Is that also in your work, that the rings will fade?
Oh, no, I don't actually. I did only one paper on rings years ago. I did some simulations of the local properties of rings, but I'm not really an expert in rings. But the spreading time, the fact that the spreading time of the rings is 100 million years means that rings spread both outwards and inwards, and so the fact that they're spreading so much inwards means they're losing mass constantly, and then the outward spreading sometimes allows small satellites to accrete. So it just gives a time scale for the evolution. We didn't try to publicize the paper, but it was, I have to admit, fun that it received so much publicity because we're explaining the rings of Saturn, and there were there's a metrics page on Science Magazine which showed that something like 250 news outlets covered this article, and there were a number of movies. There's a really fun movie which I'll forward you on the result. So it's not science to have great publicity, but it can't help but enjoy it.
All right.
Jair, I think that Chris wants to ask a question. He has the hand up.
Well, go ahead, Annette. You take over this part. You are in charge.
Chris, do you have a question?
Yes. If I understood correctly, it was the rings. The mass of the rings is less than 1% of the calculated mass of Chrysalis.
Yes. So,
is there any conjecture where the other 99% of the mass went? Is there any reason to believe that there's some object out there which is the object formerly known as Chrysalis?
No, the simulations of formation of rings from a disruption of a passing object. There are more than one. There are more than one such simulations, and in some of them, so the formation of the rings is a very inefficient process. So only about 1% of the original impactor ends up as rings, and the rest of it typically falls onto Saturn. But in some simulations, some of that debris form small satellites. So some of the inner satellites of Saturn may be a result of this debris reaccreting as small satellites. But again, we didn't simulate that. We have to rely on other people's simulations. Did that help?
I didn't see him anymore. I don't know if maybe he lost his connection at the end.
Yes, I noticed he disappeared.
Yeah, he disappeared. Sorry. Maybe another questions and we wait Chris come back.
Well, first I would like to thank you, Jack, for this very, very interesting, very nice talk. I was just curious, I heard, perhaps I heard it wrong, but did you say you thought in the modeling you thought of Saturn as a rigid body? Like for the moment of inertia, I thought that was kind of just wondering about difficulties with that.
Oh, well, everyone actually who models the dynamics of Saturn's obliquity models Saturn as a rigid body. So the Cassini spacecraft, the JPL simulations that analyze the data also model Saturn as a rigid body. But in that, there's nothing. There's not really a problem because Euler's equations are basically just derived from conservation of angular momentum. It would only matter that if there was a significant wobble. that would where you would have difficulty with modeling it as a rigid body. So that so we wouldn't expect the Eulerian notation to be correct. So the rotation of Saturn has essentially zero wobble, so it's rotating around the largest moment of inertia. And in our simulations, which allow wobble to be excited, the amplitude of the wobble is even after 200 million years is restricted to something of order 10 to the minus 9 radians. So it seems to be, I think, a good approximation to assume that it's a rigid body, just because we don't depend upon any wobble aspect of the motion. I think it is. I've talked to a number of people. It's a little mysterious to me how Saturn can precess as a rigid body, because the forces on the fluid are complicated, yet nevertheless somehow they all act together as if Saturn were a rigid body. That's a little mystery for me, and exactly how that occurs physically. But did that help, Edward?
Yes, certainly. Thank you very much.
Yeah.
Professor Jack, Chris, come back. Maybe you can repeat the end of your answer, please.
Did you hear the explanation I gave, or should I repeat it?
I heard it.
No, thank you, I did. Thank you very much.
Yeah, I think to pursue this research further, there are several things we would like to do. One is, it's another big task to simulate the evolution of the debris and really pin down exactly what would happen in our scenario. So that's something that one could do, should be done. But I think other people are more tooled up to do that than we are. And then another problem, we found that Hyperion's orbit is significantly, and in some cases significantly modified. But interestingly, the orbits of the other major Saturn satellites, Mimas, Tethys, Enceladus, Dione, they're actually not affected by Chrysalis. I think that's because the orbit of Chrysalis, by the time it has a close encounter with Saturn, is fairly inclined, so it avoids encounters with the other inner Saturn satellites. So, yeah.
With respect to what you just said about proceeding further, you mentioned that the step size that you used in your simulations, they allow simulations for, I don't know if I got it right, is 5 million years for each simulation?
The simulations that we did to determine the little gray band were plus or minus 50 million years.
Oh, 50 million.
And we integrated 5 million years per day. So those took 10 days, because we run the forward and backward simulation at the same time. And then we vary the moment of inertia. So each time we choose a new moment of inertia, we have to redo that. So we have like a bisection method to find the critical value of the moment of inertia. So it took a fair amount of computer time to determine the little gray band.
But I'm asking for the future simulations. Is there in the order of magnitude of this 100 million years, or I'm off the mark?
Oh, I'm sorry, I missed that.
I'm kind of confused. Comparisons of the time of each simulation and the time of existence of the rings. How they do compare the order of magnitude of?
Well, the backward simulations.
They are longer or smaller than this?
They're the backward simulations of the full model span to 200 million years, back to before Chrysalis was lost.
All right.
That was the blue curve, and then Those calculations took about 40 days of simulation time, and we did several of those with different moments of inertia. The time step is chosen because in these type of integrators, you typically have to have on the order of 15 to 20 steps for the innermost orbit. So that the innermost orbit is Mimas, and so that determines the time step.
So at any rate is at least double of the existence of the rings, so to speak.
Yeah, the integrations were about twice the length of the age of the rings.
Okay, great.
Mm-hmm. Well, I hope that was pretty understandable.
For sure, of course.
Yes.
Lots of
Yes.
things to think.
Any other questions or comments? Okay, so I have a question from Professor Ken. Your audio it doesn't work. Ken,
Oh, I missed. Were you asking a question? I missed that.
No, it's actually he only using the option headphone, not microphone. So you have to change it, the option, Professor Ken. Could you see a microphone, a button with a microphone downstairs, near from the bottom of the camera, etc.? No? Maybe, well, yeah, it's a maybe you have to get out and to come back and choose the microphone to ask your question.
Or send by the chat.
Problem. Or send by the chat if you want to write. Okay. I really like your heart in your chest. Okay, so any other question or comments? I will just stop to record it, and if you want to open your camera to take a picture from today, and Professor Jack, if you could to stop the presentation, please. It's really nice to see you again, guys. I will just stop to recording.